to explain the electrical changes, the first thing that you need to establish is what causes the positive and negative charges in the first place. And what causes the positive and negative charges are four categories of charged particles or ions. That will be the sodium ion concentration both outside the cell in the extracellular fluid as well as inside the cell. What is the potassium ion concentration outside the cell versus inside? What's the chloride ion concentration? And then what's the concentration of a lot of negatively charged proteins that are collectively referred to as just the anions, meaning the negatively charged particles, anions. Okay. So when these ions are analyzed, then inside the neuron, there's both positively charged stuff and negatively charged stuff. All right, what's the positively charged stuff caused by inside the neuron? Sodium and potassium ions, positively charged ions. And what's the negatively charged stuff here caused by? Negatively charged chloride ions and negatively charged proteins, called anions in general. Okay, now you got both in here, so you got both positive and negative charge in here. It's just that you got 10, 20, 30, 40, 50, 60, 70 units more negative stuff inside than you have positive stuff. 10, 20, 30, 40, 50, 60, 70. And this is why the inside measures a negative 70 millivolts when the neuron is at rest. It's not that there's no positive in there, it's there too. But it's just more negative than positive. All right, so that explains just the resting potential. Now, let's understand what happens when you stimulate the neuron. Okay? Well, you have to look at the relative concentrations of the ions. Inside the neuron. All right, so in your textbook, you will see a chart like this. And this chart is showing the actual measured relative concentrations of sodium ions in the cytosol. All right, what do we mean by the cytosol?
The inner part of
That's the cytoplasm, that's the fluid, the background fluid that's inside the neuron. Not just where the nerve cell body is, but everywhere, the dendrites as well as in the axons. That is cytoplasm, the liquid part of cytoplasm called the cytosol. Okay? And where is the extracellular fluid?
outside
That
of the
surrounds the neuron. Okay? And this shows the exact measurement of the four types of ions that make the nerve cell charge. What maintains these precise amounts outside the neuron and inside is that outside of nerve cells, there's a very special fluid called the cerebrospinal fluid, okay? And the brain and the spinal cord regulates the ions and other substances that will be allowed to cross this blood-brain barrier into the extracellular fluid, okay? And so that's what maintains these particular balances of the different ions. Now, we're taking a shortcut just to get we're not memorizing the exact molar concentration. all that we're saying is that in the extracellular fluid, there is a large concentration of sodium ions. The brackets means concentration of. So there's a large concentration of sodium ions in the extracellular fluid. But inside, in the cytosol, there's a low concentration. Okay, but with respect to potassium, in the extracellular fluid, there's a low concentration of potassium ions in the extracellular fluid, all around the neuron. But inside the neuron, there's a large concentration of potassium. For chloride ions, there's a large concentration of chloride ions outside, all around. But inside, there's a low concentration of chloride ions. With respect to these negatively charged anions that are proteins, all right, almost totally, they're inside the neuron. There's a large concentration inside the neuron, and little or no proteins in the extracellular fluid. If there are proteins leaking into the extracellular fluid, that could be a sign that something's wrong. Okay, the proteins, the anions that are proteins, are too big to move across the membrane. So they're stuck on the inside of the cell. It is the cell that makes these proteins. All right, now, so it's this setup of these ions that's going to translate into the electrical changes that we are observing in the graded potentials and in the action potential. Whatever stimulates a neuron, whatever excites or stimulates a neuron, is going to open the sodium channels first. Okay? If it's a low-level stimulus, it's going to cause the sodium channels to open a little bit, but then close quickly. If it's a stronger stimulus, then the stronger stimulus will open the channels even more. And in which direction will sodium flow in once the channels are open?
Inside.
Okay? So in all of these cases, except for the proteins that won't move across the membrane, diffusion is what's moving the ions. The ions will always be moving while doing stimulation. It's always going to be moving from higher concentration to lower concentration. That is by diffusion. Okay? Now, just to be thorough, there are two types of leakage channels that are always open, but they only allow a very small amount of the ions to leak across the membrane. There are sodium leakage channels, and there are potassium leakage channels. Okay? And so when sodium is leaking, it's going to leak by diffusion. And sodium would leak from higher to lower concentration. It's going to leak into the cell. Potassium will leak in what direction? Out of the cell by diffusion. So even though the leakage channels are always open, they only allow a little bit of sodium or potassium to leak through. These channels are very specific. They allow one thing to leak through. If this leakage was allowed to continue, then eventually there would not be a concentration difference, and you could not have work done. Okay? So as long as you have the separation of these concentrations, then you have potential energy, just like you have in a battery, in a car battery. Okay? It separates the charges. And as long as the charges are separated, then when you make the connection, charges can flow, electricity can flow, and you got energy that cranks the motor or whatever it does.